Hello there, welcome back again. Today we shall look at nomenclature of organic compounds, how we can name organic compounds, what are the basic rules that we need to put in mind. Ideally, every possible organic compound should have a name, just like how every one of us has a name, and we need and prefer to be identified by our names. Organic compounds are given names according to the IUPAC nomenclature. IUPAC nomenclature is a systematic method of naming organic chemical compounds, as recommended by the International Union. IUPAC in full is International Union of Pure and Applied Chemistry. So there are basic principles that we need to know when we are naming organic compounds. One is identification of the parent hydrocarbon chain. We need to know the parent hydrocarbon chain, and we are going to look at a few examples. And then second to that, we need to know identification of a functional group, identification of that side chain, identify the remaining functional groups that you have, identify double or triple bond in case your compound has them, and then numbering of the chain, numbering of various substances using alphabetical orders and naming of organic compounds. Before we go to that, let's look at isomerism. Is a phenomenon where two or more compounds have the same chemical formula but possesses different structural formulas. Isomers are molecules that have the same molecular formula but have different structures. Isomers are compounds exhibiting isomerism. So we have two basic types of isomerism, that is structural isomerism and stereoisomerism. However, structural isomerism is divided into four, where we have chain actually can be divided into five, but what I have presented to before you here are four. So it's divided into chain isomerism, position isomerism, and functional group or functional isomerism, and then metamerism. So when we look at chain isomerism, is a type of structural isomerism where two or more compounds have the same molecular formula but differ in the branching. This word is branching of carbon atoms. They differ in branching of the carbon atoms. Differ in branching of carbon atoms. I wanted to make it a bit clear. So in the previous slide, we just talked about nomenclature. So let us name this specific compound in this chain isomerism. We find that we have 1 carbon, 2, 3, 4, and 5. So when we look at this compound, it has carbon to carbon single bond, and all organic compounds with carbon to carbon single bond, we call them alkanes. And since it has 5 carbon atoms, we shall say it is a pentane. So we have identified the longest chain, and we see this does not have branches, and since it doesn't have branches, it is a long chain. Okay, so since it has no branch, this is a long chain, and we have identified the functional group, and we are going to name it as pentane. Pent for a pentagon, 5-sided polygon, and then ANE for a suffix that we use while naming alkanes. So we can call this a pentane. And then we have this specific structure. This structure has a branch. The branch is supposed to be here. Let me just pull it a bit. So this is our branch, and since it has a branch, the number of carbon atom reduces. So we have CH3, CH, CH2, CH3. So when we look at this, we identify the longest chain by counting the number of carbon atoms in each chain. This is 1, 2, 3, 4, or 1, 2, 3, 4. 1, 2, 3. So we find that 1, 2, 3 cannot be a chain because 4 is greater than 3. So we can either take this route or this straight route. Either of the routes, we shall find one branch, and that branch is a myth. It has one carbon atom. So we shall say this is what is the position. Put the position of the functional group. So I will say the position of the functional group. Position is 2. What is the name of the branch? The position of the branch is 2. The name of the branch is methyl. The name of the branch is methyl. 2 methyl. The name of the long chain. How many carbon atoms? 1, 2, 3, 4. So but for 4. And then since it is an alkane having a carbon to carbon single bond, butane. Since it is so but for 4 carbon atoms, 1, 2, 3, 4, and then ANE because of it having carbon to carbon single bond, making it belong to alkanes as a functional group. So that is how we can name our compounds. Okay, we are referring to the previous slides talking about nomenclature. Position isomerism is when 2 or more compounds differ in the position of the functional group or substrate atoms. For example, we can represent butanol in 2 arrangements. Butanol, when we see OL, this belongs to alcohols or alkanones functional group, and those have the hydroxyl group, OH, and this is our other hydroxyl group. We find that it is bonded to this arrow, and then we have our OH. Wow, we have our OH. Here. So these are 2 compounds. We can as well name this. Okay, so this is butanol, but, and then OL, butan, OL. And so here we can say this is but1. This one's name, we shall say this is butan 1 all, because our OH group is on carbon atom 1. We start counting from a carbon atom carrying a functional group, and this is carbon atom 1. So that is butanol, and that has affected our second example. So for the second example, we can guess by looking at, we start counting from a carbon atom carrying a functional group or a carbon atom closer to the functional group. So I will say that this is 1, 2, 3, 4. 1, 2, 3. So when I take this route, you find that OH is on carbon atom 2. When I start counting from this side, the right hand side, the OH, which is a functional group, is on carbon atom 3. So I take the one which is less, which is 2. So this will be my, how many carbon atoms? 1, 2, 3, 4. An alkane with 4 carbon atoms would be butane. Okay, but now since it has the OH group, I will add OL. However, I need to put the position of the functional group. Position of the functional group can either come before or in the middle of, just like what we did in the first. either in the middle of butane and OL, or we can start, since we use this example, let us start this with the 2-butanol. So that is how we can name. That is position isomerism. An example of a position isomer. These are isomers of butanol. These are isomers representing position isomerism. And even alkenes, carbon to carbon double bond, can undergo position isomerism. So we have functional isomerism is when two or more compounds have an identical molecular formula but differ in the functional group. For example, we can represent our CH3H6O as a ketone as well as aldehydes. So we are going to elaborate how ketones are, where we have a carbon to oxygen double bond, and then we also have a carbon to oxygen double bond and bonded to a hydrogen atom, which represent aldehydes. So we are going to, as we go on, I will give you a video concerning a lecture concerning ketones and aldehydes specifically. But functional group isomerism or functional isomerism can be represented by ketones and aldehydes. Metamerism, this is exhibited by compounds due to the presence of different alkyl chains in the site of the functional group. For example, we have C4H10 oxygen written as ethoxyethane and then methoxyethane. So these are ethers, and ethers we also name them basing on the alkyl groups that are attached to the oxygen atom. So we see that this is an alkyl group and these are two, so we shall say ethyl or ethane. So we shall name the one which is smaller becomes the prefix, and then the one which is longer becomes the parent name. However, with this, we see that the carbon atoms this side of oxygen are the same as the other side of the oxygen. Like this is 1, 2, and this side is also 1, 2. Two carbon atoms in both sides. But when we look at this example, we have 1, 1, 2, 3. So we find that this side is longer. Carbon atoms, this other side, right-hand side of oxygen, is longer than the left-hand side of oxygen. And because of that, we find that this becomes the parent, and we take the parent for the name of an alkane. And then this becomes the branch. The branch, we take the meth, the eth, we take and then add the word oxy for the oxygen. For example, for this, we have said this is ethoxy because these are two carbon atoms representing eth. Oxy is for the oxygen, and then ethane, ethoxy, ethane. This one is methoxypropane. That is metamerism. We also have tatarism as another type of structural isomerism. I will request you to read more about that and ask questions where you get defeated. So let us look at stereoisomerism as another type of isomerism. We say there are majorly two branches, stereoisomerism and structural isomerism. Structural isomerism, we have said it has functional group isomerism, position isomerism, chain isomerism, metamerism, and tatarism. And in each of them, you need to know the isomers, and then you also need to know the different functional groups that can be represented in chain isomerism, that can be represented in position isomerism, that can be represented in functional group isomerism, that can be represented in metamerism, that can be represented in tatarism. Stereoisomerism is a phenomenon in which compounds have the same molecular formula but differ in the relative positioning or orientation of atoms in space. Stereoisomerism are compounds exhibiting stereoisomerism. Classification of stereoisomerism, we see that it is classified into two. We have the geometric isomerism, is shown by molecules in which their spiral positions are locked to each other due to the presence of a ring structure or a double bond. And we have examples of cis and trans compounds that have cis and trans. And then we have optical isomerism, two or more compounds that have the same molecular arrangement but differ in the optical isomers. It is also called enantiomerism, which is defined as the superimposable mirror images. And we see that the natural example of optical isomerism is when we have our hands, our palm of our hands, when we put before us, we see that they are opposite to each other. It is like there is an imaginary mirror in the middle where you see that there is the other side of the hand, or the other hand looks to be the opposite of the other, or looks to be a mirror image. So that's a natural example of optical isomerism. So that is all about isomerism. Next, we are going to look at different types of chemical reactions. However, we had already looked at some of them in the previous video. We are just going to re-echo on those that we did not finish. Thank you so much for listening. If you came up to this far to listen to this lecture, it means you liked it and it was interesting. Please send us greetings and send us a location where you're watching from so that we can send you a special greeting in the next video. Thank you, stay tuned, and let's catch up in the next video.